Black Pearl Audio Papers presents Section 4: The Generative Capacity of Reduction Relations and its Utility for Causation. The negative thesis asserts that science is not based fundamentally on cause and effect. That is not to say that notions of cause and effect are purely fictions. That would be too severe. There is a sense in which causes are properly part of our scientific picture of the natural world, and my goal in the positive thesis is to find it. I shall urge that the place of causes in science is closely analogous to the place of superseded theories. In 1900, our picture of the natural world seemed secure. We concluded that the planet Earth orbited the Sun because of a gravitational force exerted on it by the Sun, and matter consisted of many small charged particles called ions or electrons. All of this was supported by an impressive body of observational and experimental evidence. 3 decades later, these conclusions had been overturned. Einstein's general theory of relativity assured us that gravitation was not a force after all, but a curvature of space-time. Quantum theory revealed that our fundamental particles were some mysterious conglomeration of both particle and wave-like properties. The earlier theories did not disappear, and they could not. The large bodies of evidence amassed by Newton in favor of gravitational forces and by Thomson for electrons as particles needed to be directed to favor the new theories. The simplest way of doing this was to show that the older theories would be returned to us in suitable limiting cases. General relativity tells us that gravitation does behave just like a force, as long as we deal only with very weak gravity. And quantum theory tells us that we can neglect the wave-like properties of electrons as long as we stay away from circumstances in which interference effects arise. In the right conditions, the newer theories revert to the older, so that evidence for the older could be inherited by the newer. A simpler and more convenient example is the material theory of heat. In the 18th and early 19th century, heat was conceived of as a conserved fluid. The temperature measured the density of the fluid, and the natural tendency of the fluid to flow from high to low density was manifested as a tendency to flow from high to low temperature. The theory flourished when Lavoisier in 1790 included the matter of heat as the element caloric in his treatise that founded modern chemistry, and Carnot in 1824 laid the foundations of modern thermodynamics with an analysis of heat engines that still presumed the caloric theory. Around 1850, through the work of Joule, Clausius, Thomson, and others, this material theory of heat fell with the recognition that heat could be converted into other forms of energy. Heat came to be identified with a disorderly distribution of energy over the very many component subsystems of some body. In the case of gases, the heat energy resided in the kinetic energy of the gas molecules, verifying a kinetic theory of heat. The older material theory could still be recovered as long as one considered processes in which there was no conversion between heat energy and the other forms of energy, such as work. An example would be the conduction of heat along a metal bar. Exactly because heat is a form of energy, and energy is conserved, the propagating heat will behave like a conserved fluid. In the newer theory, the temperature is measured by the average energy density. It is a matter of overwhelming probability that energy will pass from regions of higher temperature, higher average energy, to those of lower temperature, lower average energy, with the result that the heat energy distribution moves towards the uniform. This once again replicates a basic result of the caloric theory. Heat spontaneously moves from hotter to colder. Generative capacity. I call this feature of reduction relations their generative capacity. In returning the older theories, the relations revive a defunct ontology. More precisely, they do not show that heat is a fluid, or that gravity is a force, or that electrons are purely particles. Rather, they show that in the right domain, the world behaves just as if they were. The advantages of this generative capacity are great. It is not just that the newer theories could now inherit the evidential base of the old. It was also that the newer theories were conceptually quite difficult to work with, and reverting to the older theories often greatly eases our recovery of important results. Einstein's general relativity does assure us that planets orbit the Sun almost exactly in elliptical orbits, with the Sun at one focus. But a direct demonstration in Einstein's theory is onerous, since much of the curvature of space-time plays no significant role in this result. The easiest way to recover it is just to recall that Einstein's theory reverts to Newton's in the weak gravity of the solar system, and that the result is a familiar part of Newton's theory. In many cases, it is just conceptually easier and quite adequate to imagine that gravity is a force, or heat a fluid. Applied to causation, are causes real? The situation is the same, I urge, with causation. We have some idea of what it is to conform to cause and effect, although what that amounts to has changed from epoch to epoch, and even person to person. The world does not conform to those causal expectations in the sense that they form the basis of our mature sciences. However, in appropriately restricted circumstances, our science entails that nature will conform to one or another form of our causal expectations. The restriction to those domains generates the causal properties in the same way that a restriction to our solar system restored gravity as a force within general relativity, or, ignoring conversion processes, restored heat as a conserved fluid. The causes are not real in the sense of being elements of our fundamental scientific ontology. Rather, in these restricted domains, the world just behaves as if appropriately identified causes were fundamental. So, are causes real? My best answer is that they are as real as caloric and gravitational forces. And how real are they? That question is the subject of an extensive literature in philosophy of science on the topic of reduction. For a survey, see Silberstein, 2002. I will leave readers to make up their own minds, but I will map out some options drawn from the reduction literature and express an opinion. One could be a fictionalist and insist that causes, caloric, and gravitational forces are ultimately just inventions, since they are not present in the fundamental ontology. Or one could be a realist and insist upon the autonomy of the various levels of science. To withhold reality from an entity, one might say, because it does not fall in the fundamental ontology of our most advanced science, is to risk an infinite regress that leaves us with no decision at all about the reality of anything in our extant sciences, unless one is confident that our latest science can never be superseded. My own view is an intermediate one. Causes, caloric, and gravitational forces have a derivative reality. They are not fictions insofar as they are not freely invented by us. Our deeper sciences must have quite particular properties so that these entities are generated in the reduction relation. Whatever reality the entities have subsists in those properties, and the properties will persist in some form even if the deeper science is replaced by a yet deeper one. But then they cannot claim the same reality as the fundamental ontology. Heat is, after all, a form of energy, and not a conserved fluid. Hence, I call the compromise a derivative reality. Science versus folk science. A major difference between causation and the cases of caloric and gravitational force lies in the precision of the theory governing the entities and processes called up by reduction relations. In the case of caloric and gravitational forces, we call up quite precise theories, such as Newton's theory of gravitation. In the case of causes, what we call up is a collection of causal notions that do not comprise a theory as precise as Newton's theory of gravitation. That no correspondingly precise theory is possible, or at least presently available, is implicit in the continuing proliferation of different accounts of causation in the literature. Yet there is some system and regularity to causal notions called up by reduction relations. Hence, I have labeled that system a, quote, folk theory, unquote, or, quote, folk science, unquote. There are comparable cases in science in which reduction relations call up powers that are not governed by a well-worked-out but now defunct theory. The simplest example pertains to vacua. We know that in classical physics, vacua have no active powers, yet we routinely attribute to them the ability to draw things in, to suck. The appearance of this active power arises in a special but common case. The vacuum is surrounded by a fluid, such as air, with some positive pressure. The power of the vacuum is really just that of the pressure of the surrounding fluid, according to ordinary continuum mechanics. There is no precise account of the active power of the vacuum in the resulting folk theory, which is always employed qualitatively. Any attempt to make it quantitative almost immediately involves replacing the active power of the vacuum by the active power of a pressure differential, whereby we return to the ordinary theory of continuum mechanics. Nonetheless, at a purely qualitative level, it is very convenient to talk of creating the vacuum and to explain resulting processes in terms of a supposed active power of the vacuum. Causal talk in science has the same status. In many familiar cases, our best sciences tell us that the world behaves as if it were governed by causes obeying some sort of causal principle, with quantitatively measured physical properties such as forces, chemical potentials, and temperature gradients being replaced by qualitative causal powers and tendencies. This proves to be a very convenient way to grasp processes that might otherwise be opaque, just as attributing active powers to a vacuum can greatly simplify explanatory stories. No harm is done as long as we take neither the active powers of the vacuum nor the causal principle too seriously. The multiplicity of folk notions of causation. There is a second major difference. Newton's theory of gravitational forces, or the historical theory of caloric, are fixed, so that their recovery from newer science unequivocally succeeds or fails. Matters are far less clear with causation. The little historical survey of notions of causation in Section 2 and the present literature in philosophy of causation shows considerable variation in views on what counts as causal. Therefore, we do not have one unambiguous notion that must be generated by the reduction relations, but many possibilities. Moreover, the notion seems to vary from domain to domain. The sort of causation we recover in physical systems is not quite the same as the sort we recover in biological domains, for example. Finally, our notion of causation evolves in response to developments in the science. May causes act at a distance? Is causation anything more than determinism? The answers depend on who you ask, and when you ask, and those differences in part, result from developments in the relevant science. In crude analogy, seeking causation in nature is akin to seeking images in the clouds. Different people naturally see different images, and different clouds incline us to seek different images. But once an image has been identified, we generally all see it. Moreover, the image is not a pure fiction. It is grounded in the real shape of the cloud. The nose of the face does correspond to a real lobe in the cloud. This concludes Section 4 of Causation as Folk Science by John D. Norton. Please stay tuned for Section 5.